in the plane. So we're going to go over some basic definitions. You've probably seen some of this stuff, at least. And then we're going to get to some other stuff. We'll get to like circles and parabolas and ellipses. We'll see how far we get through this today. So some basic definitions. Distance. The distance between 2 points is given by this formula. So point 1 is x1, y1, point 2 is x2, y2, and we have a nice formula. I mean, if you really like memorizing formulas, that's a fine formula to memorize. I like to memorize a different formula, slightly different formula, because this distance formula just comes from the Pythagorean Theorem. So let's suppose I've got my 2 points. Maybe this is x1, y1, and up here is x2, y2. So what I really want is to find this distance, right? We do one of our favorite things to do in the plane, and that is draw some perpendiculars. So I'm going to draw this over here. I'm going to draw this down here. And when we do that, we have a nice right triangle here. Now, can we figure out, like, what should be the coordinates of this point in terms of the coordinates that we already have up here? Like, what should be the x-coordinate? x2, right? It's right below the top one, so there's x2. How about the y-coordinate? y1, because it's straight across, right, from this point here, right? This doesn't go up or down, right? It's got the same y-coordinate. And now that we know those coordinates, we can figure out these distances. Now, this is a really kind of simple idea that's going to come back over and over again. But if I want to find a horizontal distance in the plane, I just take the right x minus the left x, right? It's just a straight line that's horizontal. So this distance is x2 minus x1. And if I want to find this vertical distance here, what should that be? Say that louder.
y2 minus y1.
Yeah, top y minus bottom y. So y2 minus y1. And now all we need to do is use Pythagoras. Let's see. D squared is equal to x2 minus x1 squared plus y2 minus y1 squared, right? The Pythagorean theorem simply says that the square of the hypotenuse is equal to the sum of the squares of the two legs. And if I want to solve for d, take the square root. Now, often when I'm doing some algebra, if I'm the one imposing a square root on an equation, I'd have to be careful and indicate that there could be a positive or a negative square root. In this case, we don't have to worry about that because it's distance. It's a positive value. So we know we just want the positive root. And here we've got now the formula that's in the theorem above. One thing we're not going to do here is we're not going to say, oh, this is just equal to x2 minus x1 plus y2 minus y1. Like, the square root does not cancel out these squares. And can anybody explain why?
Because it's over addition.
Because it's over addition, right? We can't split up a radical over addition or subtraction. If it were a product or division, then we can, right? But we can't split up radicals over addition or subtraction. You get a prize, an undetermined prize right now. I'll think of something good.
I'll probably still cancel it.
Oh, don't tell me that.
I'll try that.
All right, so let's do an example. Let's find the distance between these 2 points. I'm going to start off by just calling one of these my x1, y1, and one of them my x2, y2. It really doesn't matter which one you pick, as long as you're consistent. I'm going to just write out the formula. And then I just plug some stuff in. So let's see. -1 minus 3 squared plus -5 plus 2 squared. Plus 2 because we're subtracting that -2. I'm going to be careful about the order of operations here. So what do we have? -4 squared is 16. And -3 squared is 9. So we get the square root of 25, which is 5. Okay. So, sticking with the theme of picking a couple of points on the line, we just found and kind of reminded ourselves how we might find the distance between those 2 points. We could also find the slope of the line segment connecting those 2 points. So again, we'll just think of having a couple of points, x1, y1, and x2, y2. And the slope is simply the difference in y's over the difference in x's. That's rise over run. So I spell that incorrectly on purpose. The y's go on top. So I want to find the slope of the line segment connecting these 2 points. Again, I'm going to just assign one of these to be my x1, y1, and one of them will be my x2, y2. So we have -7 minus a -5, so that's +5 divided by -2 minus 3. That gives us, what, -2 over -5. And just like with any other fraction, I'm going to simplify it, so this is a positive 2/5. Questions so far? Okay. So the slope of the line gives us a sense for, of how steep it is, like whether it falls or rises as x moves from left to right, and how steep, right? So a large slope is quite steep, and a small slope, like 1/3, is not very steep at all. But we have another way to measure how a line might be rising or declining and how steep it might be, and that is the inclination of a line. So the inclination of a line is an angle. So imagine, I'm going to draw a couple of pictures up here. So if I have, here's a line with a positive slope, and here's a line with a negative slope. But regardless of which line I'm looking at, the inclination of the lines, I see where it crosses the x-axis. And I start on the right side of that where it crosses, and I just draw the angle up till I get to that line. So there's the inclination. We'll call that alpha. And here is this inclination. What do you notice? Any similarities or differences in what we expect to get for alpha, or for this inclination, depending on whether the line is increasing or decreasing?
Increasing, that's an acute angle.
Yeah. Yep. So if the line is increasing, this angle is acute, right? It's less than 90 degrees. And if it's decreasing, it's more than 90 degrees. The inclination will always be between 0 and 180. 180 is like a horizontal line, or 0, right? I guess the inclination you could say 0 or 180 if it's a perfectly horizontal line. But once you try to move past 180 degrees, then you're back to an acute angle, right? Because it becomes an increasing line again. Now, the relationship between the inclination and the slope is given right here. The slope is tan of alpha. Now, the reason for that is really just, remember right triangle trig, like SOHCAHTOA? That is basically the only relationship we need here. So if I picked, I'm looking at the point where it crosses the x-axis, and pick another point up here. And I drop down a perpendicular, because what else are you going to do in the plane but drop down a perpendicular and get yourself a right triangle. This is, if I were to, use SOHCAHTOA on this angle, right, I've got a couple of legs, this leg and that leg. Finding the slope just requires rise over run, right? So some distance up divided by some distance over. But if I use SOHCAHTOA here, in fact, just the TOA part, we get tan alpha equals rise over run. And that's precisely what it says in this definition, where it says m is equal to tan alpha. Right? Rise over run is our slope. So let's find, in example 1.3, they give us some inclinations. We're going to find the slope. This direction is really straightforward. I'm just going to plug the angle into the calculator and see what it gives me. So here, m is tan of 45 degrees. And if you plug that into the calculator, you'll get 1, positive 1. Our next angle is 110 degrees. That's not one of the convenient angles on the unit circle, but here we can use the calculator. Let's see, I'm going to make sure I'm in degree mode. So tan of 110 is negative 2.75-ish. That makes sense that we got a negative slope. It's an obtuse angle. Now going the other way, we have to be a little bit more careful. If they give us a slope, if that slope is positive, and we want to find the inclination, that part is not so tricky as when they give us a negative slope. So let's start with that positive slope. They tell us that m is equal to 2. Now we know that our slope is tan alpha, so they're telling us that tan alpha is equal to 2. What is the tool that we have that allows us to know what tangent of alpha is and be able to extract alpha from this? Not cotan. Arctan, or the inverse tan. Yep. So if tan alpha is equal to 2, that means that alpha is arctan of 2. You might be more familiar with this notation. I tend to use the arc notation a little bit more because I find that some people are tempted to interpret this like it's an exponent, and that's definitely not what it is, so we usually use the arc notation.
Are they any different other than just being different?
They're just different notations for the same thing. So let's see, second tan of 2. I get 63.4 degrees. That seems like a plausible answer. My slope was positive, and my only sort of gauge from that, I guess, is that I'm going to at least expect it to be an acute angle, and that's what we got. Yes, exactly. So 63.4 degrees. When your slope is positive and you want to find alpha, you just use the arctan or inverse tan, and you get your answer. When your slope is negative, we have to be a bit careful because arctan will not produce a second quadrant angle, no matter how hard we try. Arctan will only ever produce angles. Let's see. So here's the unit circle. Arctan for arctan of a positive will put you in the first quadrant, like those acute angles. Arctan of a negative will always bring you down here, and it will do so by expressing it as a negative angle. So arctan always produces results that are between negative 90 and positive 90. We know we want our angle to be over here. We could add 180. I often do it slightly differently, but adding 180 is fine because you're just reflecting it across from the fourth quadrant to the second. The way I often think about this, and it's mostly I'm a creature of habit, so the way I think about it is the first thing I do is I find a reference angle. So that reference angle, I'll call it alpha ref, tangent of that reference angle is positive 0.312. So this isn't a mistake. I'm intentionally just considering it to be positive. So like here, there's my reference angle. So our reference angle is arctan of 0.312, which is 17.3 degrees. Now, what I really want is this angle over here, which is just a reflection across the y-axis. But the reason that I like using the reference angle is because that reference, that alpha ref, is the same as this angle, right? There's alpha ref. So if what I want is this angle, all I'm going to do is subtract that from 180. $162.7. But you'll get the same thing if you just found arctan of negative 0.312. That'll give you negative 17.3 degrees, as it turns out. And then you add 180. You'll get exactly the same result. At the bottom, we just have a remark about what we already observed, this connection between positive and negative slopes and whether that angle is acute or obtuse. Okay. The statement in this definition, the statements in this definition will shock nobody. They're familiar facts, parallel, they just don't intersect. They're going to have the same slope. If they have the same slope, clearly they've got to have the same inclination. With perpendicular, geometrically, we know it means that they meet at 90 degrees. That's really kind of the geometric definition. But we have another way to think about perpendicular lines, algebraically. When last time you did equations of lines, and maybe you're graphing them, or seeing if you're working with the equation of a line, how did you tell if two lines were perpendicular?
Inverse slope.
Yeah, right. So the opposite and reciprocal.
So
Yep.
2 or negative 2.
That's just opposite. It'd be 2 or negative a half,
Right.
right? Or 3 halves and negative 2/3. Right. So you change the sign and you flip them. And so algebraically, that's how we know two lines are perpendicular. Geometrically, though, that's sort of our definition here, that they meet at 90 degrees. So what I want to do right now, is just sort of connect these two ideas. And let's see. And just sort of, if we start with that geometric definition of perpendicular, can we show that their slopes should be the same? Right, so I've got two lines here. One line has an inclination of alpha 1, and one line has an inclination of alpha 2. So their slopes are tan of alpha 1 and tan of alpha 2. Our goal is going to be able to show that whatever the value, tan of alpha 1 and tan of alpha 2 are opposite reciprocal values to each other. We're going to start just by using the fact that they're going to intersect at 90 degrees up here. Let's begin by figuring out that angle. What should that angle be?
Assuming we know the alpha 2.
Yeah. In terms of alpha 2 or alpha 1.
180 minus that.
180 minus alpha 2. Yep, because it makes a straight line. It's also 90 minus alpha 1 because these are two of the acute angles in a right triangle. So 180 minus alpha 2 is in fact the same thing as 90 minus alpha 1. So I'm going to start with that equation. I think okay, I'm going to subtract 90 from both sides. So we have, well, on the left side, what, 90 minus alpha 2 is equal to negative alpha 1. Trying to decide if I want to make one more change or if it doesn't really matter at this point. I think it doesn't matter at this point. Okay, these angles are the same, right? If these angles are the same, then if I take tangent of these angles, I'm going to get the same value. So let's take tan of both sides. Now, at this point, we're going to use a fact, and I want to just sort of set you all at ease. I'm doing this so we can all see and believe and understand why there's a connection between the geometric definition of perpendicular lines and why that implies that their slopes must be opposite and reciprocal. It's not a thing where I'm going to expect you to remember always some obscure facts about the tangent function that we're going to use here. Thank you. So a couple of facts that we're going to use next is that, so if I take an angle, 90 minus alpha, take an angle, alpha 2, whatever, some acute angle, and I subtract it from 90, this is the complement of the angle, right? Because 90 minus alpha 2, whatever that angle is, plus alpha 2 is going to add up to 90. Those are complementary angles. Now, if you think about the trig functions, we've got sine and cosine, secant and cosecant, tangent and cotangent. And the reason that they have those names, like these co-functions, is because they agree on complements. So tangent of 90 minus alpha 2, tangent of the complement of alpha 2 is cotan of alpha 2. I'm going to make that substitution here. And I'll make a little note. I'm going to use another fact on the other side. And that is that tangent is what we call an odd function. And an odd function is one where there's symmetry about the origin, meaning that tangent of negative alpha 1 is negative tan of alpha 1. It's not that, I don't want us to think of it as pulling out a negative, because generally that's not something we can do from functions. It just so happens that because of the symmetry of the tangent function, if I plug in a negative angle, I will always get negative of tangent of the positive angle. Like tangent of 30 degrees, tangent of negative 30 degrees is the negative of tangent 30 degrees. That's not true for a bunch of other functions. But because it's an odd function, we can make that substitution. And now we're getting real close. How are tangent, I mean, aside from the fact that they agree on complements, how are tangent and cotangent related? Say it out loud.
They're inverses of each other.
Well, yeah,
Or
I guess you could say
reciprocals.
they're multiplicative inverses. I like to use the word reciprocal because I don't want to, like, there's different kinds of inverses. I don't want to confuse it with the inverse function. Yeah, they're reciprocal. So cotan of alpha 2 is 1 over tan of alpha 2. And now I'm gonna, I think we can do this with one more step. I mean, we can kind of maybe already see it, right? I've got a reciprocal of this is the negative of this value. Remember, tan of alpha 1 is the slope of that line with inclination alpha 1. So one way, or a convenient way I like to kind of denote this at the end, this is where I'm going to take one more step, is just, I'm going to multiply both sides by negative tan alpha 2. So on the left side, we have -1. And on the right side, we have a positive tan alpha 1, tan alpha 2. And I guess we could call this M1 times M2. Right, the product of the slopes is -1. That is another way to write that M1 and M2 are opposite and reciprocal of each other. If you multiply them together, you get -1. Huzzah! Are there questions on just how we work through this? What?
I just saw it as well.
Oh, yeah.
So this is just a relation, so this is no exact, like, angles, this is just.
Well, I mean,
when you
it's,
plug it in.
yeah, I mean, so what we've done, it's actually kind of a more powerful thing that we've done. I mean, we could have taken a couple of actual lines that we know are perpendicular, found their inclinations, and then seen that, oh yeah, their slopes are opposite, reciprocal. What we did was more powerful. We said, look, no matter what the angles are, if they, like this is true for any lines, if they meet at a right angle, we know that their slopes are going to be opposite and reciprocal. We just sort of see why. That fact that the opposite reciprocal slopes corresponding to perpendicular lines stems directly from this geometric definition of perpendicular. Other questions? Okay. All right, so let's do a problem. We're going to show that line segments joining these 3 points form a right triangle, and then we'll find its area. So when they, you know, in this chapter, sometimes they give us problems where they start out giving us geometric information and then they ask us to find some more information about it. Sometimes they start off by giving us information in the form of an equation and then asking us to find some information about it. When they give me, they don't give us a lot to go on. Like, so I just want to like observe that, right? We've got nothing except 3 points. Obviously, it's going to be enough to do this problem. So when I get started on this, if I got nothing except for those 3 points, I'm just going to plot it. Like, I want to see what this looks like. You know, it doesn't have to be perfect, but I want it to be decent. Because if I want to show that it's a right triangle, then I want to at least sort of have an idea of where the right angle is, right? And plotting it can help me do that. So just a freehand sketch, but I don't know, it looks to me like that's probably where the right angle is. So I'm going to make a little note of that. And if I wanted to show, you know, it says show that it's that this is a right triangle. So I think that's where the right angle is. How would I go about establishing that? Like, there's probably more than one way to go about establishing that, but I think there's a way that requires only a little bit of labor. Yeah, since we know, we've already established it on the last page, we know that if they're perpendicular, their slopes will be opposite reciprocal, and I've got all the coordinates, so finding the slopes will be a fairly simple process. So let's say I'll find the slope AC and I'll find the slope BC. So y2 minus y1 over x2 minus x1. I guess I'll call the C point my x2, y2 here. So that'll be 5 minus 3 on top over 5 plus 5 on the bottom, which is 2/10 or 1/5. And let's do it for the other one. This would be 5 minus 0 on top over 5 minus 6 on the bottom. And that's 5 over -1 or -5. And these are opposite and reciprocal. So perpendicular. And that means that triangle ABC is a right triangle. He asked us to do one other thing. Now we've established that it's a right triangle. Now we can find its area. And you know, there's a way to find the area of a triangle that isn't a right triangle. But when it's a right triangle, it's simpler because we can use just the one. What's that? Yeah, like 1/2 base height. Like that works as long as you know that like the height is always a perpendicular distance from the base. So if I use the two legs as the two sides I'm going to use, then I could say like, you know, this is the base and this is the height, or vice versa. It doesn't really matter. And so I just need to find those distances. So let's find that distance from A to C. Let's see, 5 plus 5 squared plus 5 minus 3 squared, and that's 100 plus 4, so we get 104. And I'm gonna reduce this. I'm gonna simplify this radical. You could, if you want, get an approximation on your calculator, but I think we're going to get a pretty convenient result at the end of this if we simplify. So, does anybody remember how to simplify a square root? Like how that process works? It's okay if you don't. But.
You have to like break it into factors.
Mm-hmm. Yep. So if I factor 104, I'm going to do that down here. So 104 is even, so I could take out a 2, and that's 52. 52 is also even. 2 and 26, and then what? 2 and 13. So we have 2 times 2 times 2 times. I've factored it all the way down to primes. So 3 2s and a 13. How do I use this factorization?
You take out 2 and 2s, right?
Yeah, so with a square root, a pair of the same factor comes out as a single factor outside. So I could take out this pair of 2's, and then what's left inside is 2 times 13, or 26. So this is 2 root 26. So there's that distance. Let's try the other distance. So x2 minus x1 is 5 minus 6 squared plus 5 minus 0 squared. -1 squared is 1. 5 squared is 25, so we get the square root of 26. Already reduced, because it's just 2 times 13, so there aren't any pairs of the same factor in 26. But this is going to work out kind of nicely. So if we find our area, 1/2 base height, we get 1/2 times 2 root 26 times root 26. You don't even need a calculator to do that one. Anybody know what we should get? 26, right? 2 times 1/2, for those canceled. And if you multiply square root by itself, we just get the number inside, right? That's by definition. If you had gone through this when you were finding these distances, and like approximated these values, so like wrote down decimal approximations, you would get something very close to 26. So it would probably be just a little